Let's start with the last session for this semester of the bank seminar. It's a pleasure to close with Camillo de Lellis from Institute of Advanced Studies in Princeton, and he will tell us about boundary plateau laws. So please go ahead.
Thank you very much. Thank you for being here. Let me just warn you that, so I guess you see my little hand, right? I mean, hovering over the slide. So I have more than one slide. I just I should have compiled like the LaTeX file another time, and then it should have shown that there are, I think, something like 34, 35 slides actually. Okay, so let me get to it. So this is about the Plateau's problem, probably known to everybody, but let me remind it anyway. So we have a one-dimensional contour gamma in the three-dimensional space, and we are looking for the surface sigma of least area which spans it. So it was actually first proposed by Lagrange in 1760. In an appendix to one of the papers in which he lays the foundation of what we nowadays call variational calculus. So how to compute Euler-Lagrange equations for minima of integral functions. But it's named after the Belgian physicist Joseph Plateau, who proposed it in the 1800 to model the shapes of soap films. So like, the experiment that you might have in mind, and which is the same experiment that I have in mind, is that you take a wire, you dip it in a bucket of soapy water, and you pull it out. And so under reasonable conditions, the soapy water will form a film, which is attached to the wire. And according to Plateau, this film is supposed to minimize the area among all possible films which kind of attach to the boundary. Give or take. Maybe it's a local minimum of the area, not a global minimum. But this is Plateau's thinking. Okay, in the 19th century, Plateau formulated what are called nowadays the Plateau laws, which, roughly speaking, they say the following. So if you look at this film, now you are in an idealized situation. So you're thinking that the film has thickness equal to 0. This is not quite true, actually. If you go with a microscope, you will actually realize that the film has a certain thickness, which is non-negligible. So it's a surface, and it's a surface which minimizes the area. And the Plateau laws say that if you're at a point P, which is away from the wire, then locally your film looks like one of the following three possible shapes. It could be locally a smooth surface. It could be three smooth surfaces which are coming together at a smooth line, forming equal angles of 120 degrees at the points of this smooth line. Or it could be a deformation of the one-dimensional cone, of the two-dimensional cone over the one skeleton of a regular tetrahedron. But not any smooth deformation. So a smooth deformation which still preserves the angles between the triangles which are forming the the two-dimensional skeleton. So here's a picture for you. With my little hand, I'm hovering over kind of the first possible model. It's a smooth surface, so it's a deformation of a flat plane. The second is easy to understand. You take three half planes that join together at a common line at 120 degrees, and you could somewhat bend this configuration, but you cannot change the angles which the surfaces form at the joining line. And here you see the one-dimensional skeleton of a tetrahedron. And maybe it's not that easy to see it, but I wanted to draw the cone over the central point. So how do I define the central point? Well, really, this is a cone with vertex, which is the barycenter of the four vertices, which are the vertices of the one-dimensional skeleton of the tetrahedron. So these, or deformations of these, are the possible local geometry of a soap film away from the boundary, away from the wire that you dipped in soapy water. Now, This was made into a theorem, into a mathematical theorem in the 1970s. It's a celebrated theorem by Gene Taylor. That, of course, to make it a theorem, you have to translate it into a mathematically rigorous statement, which is now about area minimizing surfaces. So you start with a set E, which is closed inside the three-dimensional space. And you're saying that this set is Almgren minimizing with respect to a fixed boundary gamma, which is another closed set of the three-dimensional space. If anytime that you deform your set with a Lipschitz map, you actually increase the area. Now, the Lipschitz map phi, though, with which you test the minimality has to satisfy a couple of conditions, because, of course, this would otherwise be false if I take a Lipschitz map which puts everything into a point. But the Lipschitz map is required not to move your boundary gamma, which means that actually Almgren requires phi to be really the identity in a neighborhood of gamma. And also outside of a compact set, so that you don't move things which are outside. But then the other requirement is that you don't move anything else which was outside gamma into gamma. So this is mathematically stated as, if you look at the image of the points which are displaced by the map phi, they must have positive distance from gamma. Now, of course, also to make this problem meaningful, we are assuming your set E as finite Hausdorff two-dimensional area, right? I mean, or two-dimensional measure. Otherwise, infinite sets, we're not going to consider them. Okay, so now why actually did she pick Almgren minimizers? So, in fact, you see the surfaces that we're dealing with, they're not like smooth-oriented surfaces or like even smooth unoriented surfaces. So we need to understand what it means for a film to span a contour gamma, if it is just a general closed set E. Now, there are several proposals. So for instance, the oldest one is the one from Reifenberg, which gave a definition for this using algebraic topology. There are actually new ones which came in the last 20 years. There's one from Harrison, another one from David. But one of the things, and maybe I should say, there's been actually quite beautiful work by Maggi, Stuvard, and collaborators in which they point out that, in fact, if you're trying to explain the physical phenomenon, you would need some theory which takes into account the thickness of the surface, because it's really non-negligible. And so the fact that you're minimizing area among all surfaces which are objects with zero thickness should be understood as a limiting variational problem for more realistic variational models in which you actually take into account the thickness of the surface and the fact that there's a little bit of soapy water actually inside the film. But anyway, so what is interesting is that all of these models, they all satisfy this Almgren minimizing condition. In other words, if I state to use something like the Plateau laws, which look like a regularity theorem, if I state it for something which is for a minimizing condition which is satisfied by any of your theories, of course, I've proved a general regularity theorem which is going to apply in all of these cases. And I don't even need to kind of dispute with you whether you picked up the correct notion of what it means to span a contour gamma for your set E. Okay, now note another thing. So you might actually ask, but why aren't you taking the easiest of all the possible definitions? So why don't you take classical oriented or unoriented surfaces which are bounding that gamma? For instance, if gamma is a curve, is a closed curve, and you minimize in that setting. And the reason why we're not doing that is because there are very powerful theorems dating back to De Giorgi and for boundary regularity to Hard and Simon and to Allard, that if you do this with classical oriented surfaces or unoriented surfaces, you actually find minimizers which are completely smooth. So you will not see the second and third geometric models predicted by the Plateau laws if you actually minimize among oriented classical surfaces or unoriented classical surfaces. So if you want to capture some of the physics of the problem, you actually need a variational formulation which goes beyond that of classical oriented surfaces. And it's not a closure problem. I mean, like, if I close using oriented or unoriented surfaces and I use the theory of currents, I'm still getting a minimizer which is fully regular inside and at the boundary. Okay, so what is the theorem of Taylor? So the theorem of Taylor is that if E is Algren minimizing with respect to this boundary gamma, and you fix a point P which is not on gamma, then in a sufficiently small ball, your set E is diffeomorphic to one of the three models that we just saw of the Plateau laws. Okay, so the question that I actually want to focus my talk on is that of boundary regularity. So is there a analog of the Plateau laws for boundary points, and can we actually build or can we prove an analog of Taylor's theorem at the boundary? And to my surprise, when I started actually thinking about this problem, it's largely an untouched problem. I mean, there are some contributions in the mathematical literature, but even in the physics literature, there's not like anything which looks like a Plateau statement. So now, before we go on, let us throw some assumptions on the boundary of our sample, so on the wire that we dip in the water. Well, the assumption that we're going to take is that gamma is a regular curve around the point P. I mean, the boundary regularity is a local question. So if gamma somehow makes singularities far away from P, all that I'm going to say will be not affected by this. Now, regular doesn't mean that it has to be too regular, like a C1 alpha curve surfaces, I don't know, C2 curve maybe is more relaxing of a condition to deal with, but we don't need many derivatives. Now, if you have a regular curve at P, one object which will play a pivotal role in the rest of the talk is the tangent line to the curve gamma at that point. And I'm going to denote it consistently with this letter L. Okay, now if you are in that setting, there's a very powerful theorem by Arlard which actually says that if you rescale the set E around the point P, these rescalings, these zoomings, are actually converging to minimizing cones. More precisely, if I take any sequence of radii rk going to 0, I move the point P to the origin by making a translation, and then I apply an homotety of scaling, which is the inverse of rk, in such a way that if I look at a small ball of radius rk, this will be actually zoomed into a ball of radius 1. Okay, then up to subsequences, I am converging to an Algren minimizing surface or closed set, which is a cone. And now it's a cone with respect to a boundary, which is your straight line L, which was the tangent to your gamma at the point P. Now, these limits are commonly called tangent cones. Now, here's the problem that for the first problem that I want to kind of analyze. Of course, this, like, you know, maybe I should have said this theorem of Allard works at the boundary, but it was long known even before Allard that monotonicity and formula and the existence of tangent cones holds in the interior as well. So it's not a surprise that whatever model you think of seeing for your surface locally, this model has to be a perturbation of the cone. And so therefore, the first thing that you want to do if you want to understand what kind of Plateau laws you have at the boundary is to classify all of these possible area minimizing cones with respect to a boundary L. Okay, so being a cone means that it will be invariant under rescaling. I will actually assume that it has locally finite area. This also is a consequence of the theorem of Allard. And I will then assume that it is Algren minimizing with respect to the boundary L, which is a line going through the origin. Now, observe though that I'm kind of not telling you something interesting. So I'm not telling you, even though it looks like, a very obvious assumption, that my boundary line L is actually inside your closed set E. In fact, in general, because E is a closed set and it's a cone, the relative position of E and your line L consists of three possibilities. Either they intersect only at the at the origin, or they intersect into a half line, or they intersect in a full line. Now, intersecting in a full line seems to be kind of the most obvious assumptions that you want to throw in, because it essentially means that your object is, or your soap film is really attaching to the wire. But when you run experiments, it's not that obvious that it always happens. Actually, sometimes it does happen. And so it's interesting to study also the other cases that the film, for some reason, ignores a portion of the boundary. Maybe it goes through, maybe it only wets a half of it. But anyway, so the most interesting thing is actually the one that is highlighted in red, and I'm going to make actually this assumption. This assumption is like to say that your film wets the whole boundary, and it's actually an assumption which is stable under the rescaling of Aldar's theorem. So if you started with a film which was wetting the whole boundary, you actually zoom in and you have a tangent cone which is wetting the whole boundary. Okay, so these are then what I would call the boundary plateau laws, which I'm proposing with this talk, and which will appear in a paper which is maybe like a month away of proofreading to be on the web. So if you have in R3 an angle minimizing cone with respect to this line L, then if the line L is inside E, then E belongs to a specific list of 6 families of cones, which I'm actually going to tell you next. Now, note that this is not an if and only if. I'm only telling you if you are a cone, you must be a subset or an element of these 6 geometries. We don't have the other direction. So we cannot prove that any of these elements is actually minimizing, but we have very strong indications that they are, in fact. And so that our list is really complete, and you cannot make it shorter. Well, first of all, there are 3 easy geometries. So there's a half plane, which has the boundary L. I mean, my line L will always be red in these pictures. I could have 2 half planes which share the boundary line L as a common boundary. In this case, the angle between the 2 half planes has to be bigger or equal than 120 degrees. It could be 179. It could also be 180, and it's effectively a single plane which is going through the line. Then there are actually 3 half planes coming together, as it happened in the interior. But in this case, what might happen is that the boundary line is exactly the line where the 3 half planes actually meet together. These are easy to figure out. And they are all minimizing. Another thing which is easy to figure out is that if you actually take the tetrahedron, so the one-dimensional skeleton, the cone over the one-dimensional skeleton of the tetrahedron, it contains lines. It contains exactly 3 lines passing through the central point. These are the lines which are going through the midpoints of edges of the one-dimensional skeleton, which are opposite to each other, or edges which do not share a vertex in common. Like this is one midpoint and this is another midpoint. And of course, because the tetrahedron is minimizing in the interior, it's actually minimizing even at the boundary. And now it becomes more interesting. So another thing that actually might happen is that you have the skeleton over a one-dimensional, so that you have the cone over the one-dimensional skeleton of a cube. Now, such cone is invariant under a reflection on the origin. So there's actually infinitely many lines which are going through it. So for instance, you could take as one line the diagonal of the cube, But you could also you could move the diagonal off a little bit. You could also like make the other extreme case in which the line is going through the midpoints of two opposite edges, right? Now, we know that this configuration isn't minimizing in one of the two extreme cases because we can write a competitor down. And the extreme case in which it is not minimizing is where the line is passing through the midpoints of the edges. But it looks very much minimizing both by experiments and numerical computations when the line is on the diagonal. And in fact, because no minimizing situations are open and minimizing situations are closed, you expect that you're not minimizing when you're too close to the other extreme case, but you do see from numerical experiments and simulations that it seems minimizer when you're sufficiently close to be a diagonal. So presumably there's or it's very like tempting to conjecture that there's a critical distance to the vertex for this point P, so that actually the configuration is minimizing on the interval when the distance is 0 up to this critical distance. Okay, and then there's actually something which we've not seen anywhere. So it seems we are the first ones to actually draw these pictures. Oh, by the way, maybe before we go there, before we go to the 6 family, let me show you an experiment in which you see I dipped in soapy water the one-dimensional skeleton of a tetrahedron plus a boundary line, which is this thin string, which is connecting two vertices. And you see from this picture that it really seems like the film formed a cone, right? A cone centered on the midpoint of your diagonal, which is, of course, the barycenter of the cube. Now, this is the last geometry. So this is a beast which we call thin fish. I mean, you see that the link of the cone consists of 1, 2, 3, 4, 5, 6, 7 arcs. I've drawn these edges not as arcs, but as straight edges, just because it's easier to visualize. But remember that we are cones. So, of course, a cone contains the straight edges because it will contain all of this kind of flat portion. So you see here how so these points V1, V2, V3, and V4, they are actually 4 points which form a square of a cube. But then you join two opposite vertices by going around the sphere. So like the cone is getting a big portion of a planar disk in here, going all the way around. And then they are kind of smaller triangles. I mean, like there are 6 smaller triangles over here. You see that there is a one parameter family of these cones because there's 1 degree of freedom, which is making this gamma 6 arc very short until P1 almost collides with V2. In fact, in the extreme case, you can take just P1 equal to V2. Or you can take it sort of pretty long. Of course, not too long, because when it gets to the maximal length, it's actually the time that P2 is going to hit V4. All of these edges actually meet at the vertices at 120 degrees. And P1 and P2 are the 2 points where my boundary line intersect the sphere. So these guys, they all look minimizing. Again, we have numerical simulations to show this, but we also have a lot of experiments. So this is an experiment in which you're dipping one of these guys. As I said, I have the freedom of making the geodesic arcs actually straight edges. But then, of course, something funky happens over here because I need here a geodesic arc which is going all around. So I've picked up this point over here, and then I've drawn straight edges. I don't know how easy it is to see that you really get all of the portions of the films which I showed you in the picture, but so there's a film, for instance, over here, but those ones are maybe more apparent. I mean, the ones which are kind of vertical. The horizontal portion of the film is maybe not so easy to spot. As before, this one is the boundary line. You might have noticed that in my experiments, rather than the kind of external frame is in plastic and it's 3D printed from a printer, but for the boundary, I've actually preferred to take a string and kind of attach it to the edges. And the reason why I prefer to do that is because I cannot 3D print something which is too thin, because then the object would become too brittle. On the other hand, I don't want the thickness of the boundary to influence my experiment. And so for what is the portion of the boundary that I really care, because you see the central point, of course, is this point over here. So for the line L, I prefer to attach a very small string, which is very thin. So here are some other experiments. You're seeing the same sample from another angle. Here you're seeing a sample in which these two arcs are both non-trivial, right? I mean, in the previous experiment, this one was really trivial. So this one was as long as possible, and this one was degenerate. And okay, you can see one of my lab assistants. In fact, it was not so easy to convince my third son, Gregorio, to stay, like, not to kind of shake this thing around, but it was also useful to see that in spite of the fact that he was like, shaking and like, moving this thing around very abruptly, the film is in fact extremely strong. So it stays there. It doesn't disappear. It doesn't pop. Okay, so let me give you some ideas of the proof. That's like, the remaining part of the seminar. So the proof actually combines a rather long theoretical pure math part. It's not, it's not the monstrous size of some of the works that we see actually in mathematics nowadays, especially in our areas, but it's still more than 100 pages. But it has also a lot of assistance from a computer, in fact, with many lines of code. And we use tools in several areas of mathematics, which actually made this work quite a lot of fun. So, of course, spherical geometry, as you might imagine, I will explain immediately. But anyway, the link of the cone is made by geodesic arcs. So spherical geometry is obvious. Graph theory, you can imagine, is going to play a role as well, because if you take, this link of the cone, its topology can be described as an embedded graph in the sphere, because, of course, the geodesic edges have nodes where, they join, forming equal angles. Lie group theory and isometries of the spheres, this is also something that you might imagine could be useful. Now, what I don't think certainly I wouldn't have imagined that this would have been useful. Computational algebra, and in particular Grobner bases, were useful for some conclusions. Low-dimensional topology, and especially two-dimensional simplicial complexes. And this also I wasn't imagining it's going to play a role. And of course, a lot of geometric measure theory, but that's like because it's the subject in which we're working. Okay. Last but not least, we actually do face computational challenges. So these computer-assisted portions wouldn't work, or at least didn't work immediately with the first ideas we had for coding. And the reason is that things were pretty complex, and they would run out of computational power either in the memory or in the time that actually the computer needs to finish the algorithm. So we were sometimes stuck simply because our first idea on how to program the computer assistance of the proof simply wouldn't finish in a reasonable amount of time. So the first theoretical consideration that you have is that because you have Taylor's theorem, if you pick a point which is away from the boundary line because of you have the conical structure, which makes you invariant under a dilation, so which at all effects means that at every such point you have an half line which is joining your point, connecting to the origin, which is inside your cone. You actually know that you cannot see the geometry of the tetrahedron outside of the boundary line, of course. I mean, on the boundary line, I just showed you that that might happen, but in fact, it can only happen at the origin. So this means that your link of the cone is actually a geodesic net of a particular kind. So it is formed by geodesic arcs, which are connecting vertices. So they are pairwise disjoint geodesic arcs, or if you want, any two of these geodesic arcs can only have intersection at the extrema. They connect vertices. There are two special vertices, and these are the two antipodal points, P and minus P, which are the intersection of the sphere with the line L. At this point, there must be at least one edge arriving, but there might be also 2 or 3 edges arriving. So there's this these 3 possibilities. On all the other and if 2 arcs arrive at one of these points, P or minus P, they have to form an angle which is bigger or equal than 120 degrees. I mean, this is not part of Taylor's theorem, but it's easy to see by using standard tools. Of course, this means also that if 3 arcs arrive, they have to form angles of 120 degrees, because each of them have to form an angle which is at least 120, and the sum of the 3 has to be 360. Now, at all the other vertices, the graph has always degree exactly 3, and the edges form equal angles. So this is an example. I really drew so this is an example which is exact. I mean, by using TICTC and LaTeX, you can really draw the exact perspective of one such net. So you see that on these points, on these vertices, you always have 3 of them, or these geodesic arcs coming, forming 120 degrees. And then in this particular case, you have just at the point P1 and the point P2, which are the points P and minus P, just one single edge actually arriving in there. Now, once you actually see a net like this, one thing which looks kind of natural is to, okay, so maybe first I should actually say something else. Okay, so what could be now, once you actually make this observation, a possible strategy to prove your theorem? Well, first of all, you could classify all of the geodesic nets with these particular properties. So they wouldn't necessarily be minimizing. I mean, these are more like, stationary cones. And then you could try to discard all the ones which are not in our list by exhibiting a competitor which is gaining in energy. So by truly using the minimizing property. Now, that's a good strategy. And in fact, it's the strategy that Jean Taylor actually uses in her work to classify the area minimizing cones in the interior, so away from the boundary. But in that case, because you are away from the boundaries, there are no special points P1 and P2. So those ones are not there. And so you really have a geodesic net where any vertex has degree 3. And all of the edges are coming over there at 120 degrees. So points P1 and P2 would be absent. Now, it's actually the presence of these 2 points, P1 and P2, or P or minus P, which make our theorem extremely challenging, and why it actually takes us so long to prove it. Well, first of all, in the case of Jean, she actually didn't have to do the first part of the classification. So Aladar Hepes in the 50s classified all the nets. In fact, classified even more nets. He classified all of the nets that he called isogonal, which means all geodesic nets which have the same degree at the vertices V, and with the property that the angles formed at the vertices are all the same. In particular, there are the one in which the degrees are trivalent, and so in particular the ones that we want to classify for this particular problem in the interior. So it's a beautiful work, absolutely gorgeous. It uses very clever inequalities and symmetry considerations, and it turns out that there are actually 9 such nets, and they are all rigid up to symmetries. So there's no one parameter family of these objects. I mean, they're all kind of isolated. Of course, you can move them around by using isometries, but otherwise, up to isometries, there's really just 9 of them. And most of them are not area minimizing, of course. There are 9. So Jean actually had to exclude 6 of them. And then, the 3 remaining ones were the minimizing ones of the Plateau laws. Now, in our case, there are not 9, but 30 of them. Although I should be somewhat careful about this. So among these 30, there's like 24, 25 that we can construct by hands. And so we are sure they're there. The other remaining ones are actually approximation given by the computer. So in principle, it's not like we are proving they do exist. We're just proving that they plausibly exist, and we have a good approximation for, say, the position of the points. You might also have noticed that they actually come as non-rigid. So the thin fish already is not rigid. It was a 1-parameter family. The cubes were not rigid. I mean, in principle, they are rigid, but the position of the line is not. But okay. Maybe you could argue in that case the support of the cone is anyway rigid, but for the thin fish they are not. And actually, there's even a 2-parameter family of them, and you already saw them. So I've shown you this picture. So in this picture, there are 2 degrees of freedom. So these V1 and V5 and V3, V6 edges are on the same equator. And the length of one of these edges is free. And the distance of this point P1 to V2 can also vary. So there's there's actually 4 edges which are not determined. The others are determined. And you need to decide the length of 2 of these 4 edges, and then the entire configuration is determined. But there's like a 2-parameter family of them. Okay, so how do we go now with the first part, say the classification of the stationary ones, so the ones which are 30? Well, as I already kind of hinted, for every possible link that you have, you can associate a topological object, which would be a graph embedded in the 2-dimensional sphere. That's very natural to do. So this is, for instance, the graph which is associated to the example which I gave you, in this picture over here. You see that there's a square over here, and this is the internal square, and then there are kind of the edges to the 2 special points P1 and P2, and then there are these other edges which are departing, and then you have these things which are connected. Of course, instead of being a spherical embedding, in this case, it's a planar embedding. But the planar embedding of the graph and the spherical embedding of the graph is essentially the same thing, because you can take a point at infinity for the plane and compactify it into a sphere, or if you have a sphere, you can remove a point. So the first thing that you actually realize is that there are simple topological considerations which you can leverage from Gauss-Bonnet theorem that immediately tells you that the topologies that you find are finitely many. And that's a great news, right? I mean, because if it is finitely many, it means at least you have a finite problem to consider when you look at all the possible topologies. Now, it's finitely many, but they're many. They're not that few, just out of considerations like Gauss-Bonnet. So one first thing that we did is we kind of wrote a computer code to enumerate all of the possibilities. And the computer code, it's one of the places where we had actually computational challenges at a certain point. So the algorithm needed a lot of memory. So it didn't finish in the laptop of my collaborator, Federico. It finished on my laptop just because I had twice the memory. But so this was lucky. Anyway, the computer code actually tells you, and of course, I mean, you write the computer code, but there is a theoretical part, right? I mean, the computer code is an algorithm which, because the topologies are finite, you know it's going to finish in finite time. But of course, you need the theory to actually prove that your algorithm is really exhausting the list of all the possibilities. And that's where graph theory enters. I mean, it's not an obvious thing in graph theory. Now, the list actually that the computer produces is pretty big. It's like 3,000 elements, around 3,000 elements. Now, of course, many of them, you know, it's not going to be realizable. There must be geometric reasons which are deeper than just Gauss-Bonnet. So we started having more and more sophisticated considerations on spherical polygons or on spherical geometry with pen and paper to actually kind of give conditions which would exclude some of these topologies. I mean, for instance, one thing is already written in the paper by Hepes. If you have a quadrilateral with internal angles which are 120, if you have a pentagon with internal angles which are 120 degrees, this pentagon cannot have an edge in common with a triangle which has internal angles of 120 degrees. And you can imagine that this is going to be useful in many situations because you see your graph on the sphere or your net on the sphere is splitting the complement into polygons, into spherical polygons. And so considerations about what these spherical polygons might do are going to be powerful criteria to actually exclude some of the topologies. So we did this, but even with very complicated proofs, we never were able to pass kind of with 80% of them, we could discard, maybe a little bit more than 80%, something like, I don't know, 15, 16%, but we were left actually with around 500 cases or so. So that's when actually we decided to use more spherical geometry, but combining it with, again, the assistance of a computer. So one thing which was extremely useful for us is that the considerations of Hepes' paper, which are some inequalities between the edges of these polygons, are actually quantifiable. You can write inequalities which kind of between the lengths, which kind of put a relation or a restriction. If you have a pentagon with angles of 120 degrees and there's one edge which is too long, then there must be another edge which is actually sufficiently short, something along this line. This actually helps in a lot of situations, but not everywhere, because some of the polygons that you encounter in the complement of the sphere actually don't have all angles of 120 degrees, but they're not even convex polygons. And so you need conditions to understand whether, given the edges, the length of the edges and the angles that you form, whether this actually closes or not, if you want. So this is not surprising once you actually write it down, but it's actually possible to write a closure condition for a spherical polygon, which is not, which is general, not necessarily convex, as a system of algebraic equations, which can actually be expressed very elegantly in an identity for quaternions. The way to understand this is that instead of thinking that you have a polygonal path, which is closed, think that you are traveling along the path. And while you're traveling along the path, realize that this is equivalent to actually make the points on the path slide with a rotation of the sphere while you are actually fixed. So the fact that the polygon is closing is at all effects equivalent to a composition of certain rigid motions of the sphere being equal to the identity, because at the end of the loop, you actually come back to the point itself. And rotations of the three-dimensional space are actually easily parameterized by quaternions, and the composition of the isometries are actually products of the quaternions. And so this tells you that there is a quaternionic identity, like, the multiplication of certain quaternions has to be equal to the number 1 for the loop to be closing itself. And this actually gets you an algebraic system of polynomial equations in the cosines and sines, if you want, of the length of the arcs, which actually tell you that the problem you're trying to solve is equivalent to solving a complicated yet algebraic system of equations in cosines and sines, which would parameterize. So at all effects, classifying these cons is equivalent to understand a certain specific family of real algebraic varieties with quite a few, in somehow large spaces. And of course, algebraic varieties, which are like, solutions or zeros of a system of polynomial equations of a very high degree. It's unfeasible to actually try to solve this system because the degree is simply too high. But from time to time, when you actually want to infer certain conditions on the nets, which you maybe are not good enough to infer by just using geometric considerations, tools from algebra might actually be useful. Because, for instance, maybe a symmetry of your net, which you're trying to prove, is equivalent to a certain symmetry in the roots of the polynomial equations, which you might be able to get by using algebra tools. Now, one of the interesting things is that the system is actually overdetermined. So the reason why the solutions are rare is because you have more equations than unknowns. Now, in the case of EPES, so for the classification in the interior, you actually have 3 more equations than unknowns. And that's why you only have 9 solutions, in a sense. In our case, the system is overdetermined, but there's just 1 equation more than the number of unknowns. So, and that, in a sense, is the reason why we believe we get so many solutions. So, like, 30, and why they come with multi-parameter families. I mean, when they come with multi-parameter families is because even though the system looks like overdetermined, some symmetry considerations actually kind of makes some equations equivalent, and so you can actually discard them. And sometimes when you have 1-parameter or 2-parameter families, you actually end up with an underdetermined system in that case. Okay, so now with this theory, we actually produce a computer algorithm, and the computer algorithm does the following. So it takes a topological graph, it takes a tolerance delta, and it tells you one of the 2 possible outputs. So one output is that maybe there is no possible geodesic net with that topology as we're looking for. So we can just simply take that topology and throw it away. Or there might be, when there is, actually the algorithm predicts the length of the edges with an error which is less than the accuracy delta that you have given. So that's, of course, the theoretical algorithm, which is implemented in the computer. Now, the practical implementation does not allow you to take a delta which is too small, because if you take delta which is too small, then the computer simply wouldn't finish in a reasonable amount of time its investigations. There are 2 important ingredients from pen and paper to make actually the implementation feasible. So one is that you need an effective lower bound for the length of the edges. And actually, this cannot be achieved for every edge. But the only edges which are special are the ones which are connecting to the 2 antipodal points, which, if you take them away, all the other edges have to be bounded away from 0. So, like, with an effective bound, they cannot become too short. And the reason why this is extremely useful is because for a computer, 0 and a very small number is practically indistinguishable. So having this effective lower bound makes our implementation feasible. Another important point is an hard estimate on the propagation of errors when you're composing with these isometries. I told you that the closing condition of a general polygon is equal to the composition of a certain family of identities to be equal to 1, a composition of a certain family of isometries to be equal to the identity. Now, the algorithm doesn't know exactly these isometries. They only know it only knows the isometries up to an error. And this error might be dangerously propagated, and at a certain point, in some situation, if one constant in an inequality becomes too large, our algorithm becomes computationally too heavy to get a delta which is reasonable. Okay, so this is actually what gives us this list of 30, which I told you at the beginning, of which, of course, then we want to get to 6. But this is now a list of 30 in which, say, 24 have to be excluded on energetical ground. So this is a partial classification yet. Now, there's one important point, though, which I am kind of sweeping under the rug. The families which are multi-parameter, those in principle could go into the algorithm, but the algorithm would actually have to be run several times to give plausible, this delta tolerance approximation to the infinitely many solutions that you actually have. And this would mean actually running the algorithm over and over again. So luckily, the hardest cases, so the most flexible ones, are actually classified by pen and paper mathematics. So we don't need the computer. And we actually use the computer in the cases in which essentially the net is unique. So it's rigid, and so the computer just runs once, finds the approximation, and then it actually is run another time to show that within that tolerance, the approximation it found is essentially the only feasible solution. Okay, so here, when we actually do these human pen and paper computations, sometimes we need to prove some symmetries, and most of the times you're actually able to do it with synthetic arguments. But there's a couple of situations in which we resorted to the system of polynomial equations, and we did actually algebra computations. Okay, now we're getting almost there. So you would like actually to exhibit competitors, for these other 24. And it's a rather delicate process, actually, because there are some cases in which the cone is very close to be minimizing, even though it's not minimizing. So there are some cases in which we exhibit competitors which are gaining like 1% in area. So actually these competitors are produced by using Brache's surface evolver. So at this point, it looks like the theorem is actually being proved for you. You have your cone. What we do is we perturb it a little bit. Of course, the cone is stationary, so if you actually run Brache on the cone, it's not going to change. But you perturb it a little bit, you run Brache, and you hope that at a certain point, Brache converges towards, maybe the true minimizer or another local minimum, and this is better than the cone you started with. So this is excellent, and it works, but there are two subtleties. So the first subtlety is that we do not exactly know the net, right? We only know it up to some approximation. So we need to prove with pen and paper that if you show me a competitor for the approximation, then I can actually transform it to a competitor for the theoretical net, which I don't even know if it exists, but I know that if it exists, it's nearby. So this needs pen and paper to be done. But most importantly, if you want this to be a proof, you actually have to be sure that Brache's code is not running into bugs. In which sense? Well, you had a boundary condition, right? So you had your, say, cone, which had a certain boundary, and you're not allowed to actually change the boundary. So if along the evolution, the code is not changing the boundary condition, which is what the implementation of the code by Brache certainly would promise you, the final object is actually a valid competitor for you. But the problem is that this would require you or anybody checking the proof to actually go through all the code of Brache, which is pretty long. It's also old. I mean, it was written back in the end of the 80s, beginning of the 90s. And we know for a fact that it actually has some bugs. I mean, they are not serious bugs, but we know it has bugs, because sometimes it gives you answers which are simply not plausible. Like, it's supposed to actually find some sort of approximation of a minimal surface, and it gives you spiky objects. It happens rarely, but sometimes it happens. So how do we fix this? Well, so here pen and paper comes again. So what we really care about is the competitor, which actually Braque spits at the very end. Now, this competitor is something that you can actually find from Braque software. It's a triangulated surface. So it's a number of triangles put in the three-dimensional space. They form a triangulated set, or if you want, they form a piecewise linear immersion of a simplicial complex. Now, you could hope that if you have the topological description of the simplicial complex, you have the actual description in points, you can run some verifications using two-dimensional topology or low-dimensional topology and prove that it respects your boundary condition. In fact, it's kind of subtle, because if you remember my definition of what are the admissible competitors, I actually need to produce a map. This map, which is Lipschitz, which is mapping your cone into the competitor and which is kind of respecting certain conditions compared to the boundary. And this can be done. And of course, in order to be done in such a way that we don't have to check all of these conditions by hand, we need again to devise a computer algorithm and to let actually the program go through the computer go through the triangulated surfaces which are produced by Braque and check that they satisfy these conditions, which then ensure the existence of the Almgren map. And so, of course, the area or the computation of the area of these guys is a very simple elementary thing, because they're just triangles, and the error that you do over there is essentially negligible. And then you actually proved at the end of the day that all the ones that you wanted to discard are discarded. Okay, so this is actually what I just said in words. You want to produce a map. Let me actually finish by, first of all, acknowledging the Simons Initiative on the Geometry of Flows, which has supported this research. The two engineers in Germany from the University of Passau, who kindly actually printed a lot of 3D models that we used to experiment. I mean, you saw some of them in the pictures. So these are Michael Niedermayer and Dörte Rüwele. And several discussions with Guy David, Jonas Hirsch, and Simone Steinbrüchel, which were of fundamental importance actually for us during this research. I am essentially finished and I'm running out of time. I had the slides with open problems, but let me skip that and let me go to the thank you for your attention slide.
So thanks a lot for this, telling us about your amazing work. So is there any questions? So
just one. It's maybe a rather simple question. It's only to be more specific about the topologies that you find with the computer within a tolerance delta. Does that proof or assisted proof tells you that they might exist such topologies, or at least one, or for sure there's a topology that exists within that tolerance?
Yeah, so right. So the computer tells you if there is a solution. In your net you have each segment has a certain length, and the computer tells you if there is a solution. I can predict the length of these segments up to an error which is less than delta.
Okay, but now, you have to assume that there's a solution.
It doesn't guarantee you that there is a solution. I mean, maybe, it could happen that if you ask them to do delta divided by 2, maybe it doesn't find any solution. So in a lot of the situations, we can prove with pen and paper that there is a solution. But if you really want to prove that there is a solution, you need to do something with pen and paper because the computer is only giving you an approximation. I mean, in some cases, what you could do, for instance, maybe because you have a very good approximation, maybe you can factorize your polynomial for the system of polynomials equations. And maybe you discover that you have to be, I don't know, a zero of a smaller one. But okay, in general, this looks a tall order. In some situations, the computer actually is telling you that it looks like there is a solution. But you have to beware if you are in some case in which some of the conditions start being degenerate. I mean, I already addressed one of them, which is if the length of a segment becomes very small. But there are also other degeneracies in the kind of like, space of possible solutions. And so it's not also completely clear if the computer tells you that there is a solution that you can really, or that there seems to be a solution that you can really believe it. But okay, so all of the degenerate situations we can check with pen and paper. And what remains really seems genuine. I mean, really seems like, all of them, there is a solution. I mean, like, I mean, the degree of accuracy of the computer can be pushed to a delta, which is very, very small. So, and if you are away from the generations, I think it's essentially an almost sure thing that there is a solution over there. But it's not a proof that it exists.
Okay, thanks.
But then, of course, it's important. All the ones which, for which we have this uncertainty are the ones which will be excluded on energetical grounds. So the proof actually then tells you like, well, okay, I don't know if there is a solution or not, but if there is, this net nearby has almost the correct angles. For them, I will produce like, a competitor which gains, I don't know, 0.1 in area. And this gain in area is too much. I can deform my competitor even to your theoretical, I don't know, or if it exists or not, solution. And it cannot be a minimizer because I exhibit a competitor which does better in area.
Okay, thanks. John is having also a question.
Yeah, hi. I wondered if you're familiar with the dual picture of the Heppisch classification. These nets are dual to convex deltahedra.
Yes, I am. So actually, I tried to. So when I did this, like when we were finishing, when we were finishing the first part, I actually saw a person I know in Hungary who actually worked with Heppisch, and I know personally, and I wanted actually to meet Heppisch, and this guy actually told me like, oh, unfortunately he died like 2 years ago. And then he told me, oh, but are you aware the classification of Heppisch actually follows immediately if you go to the dual of the convex body. Maybe it is of help in your problem too. And so here's where I discovered actually that luckily Heppisch didn't notice this because our, the complement of our net is not made of convex polygons. So I can't use duality of convex polygons, and I don't know what to do with the smart proof, which I think was maybe pointed out to him by Coxeter. So
yeah, I think the history is somebody wrote a paper in Dutch. It's the only math paper I've ever seen in the Dutch language, classifying the convex deltahedra, and then Coxeter reviewed that for MathSciNet and pointed out the connection.
Yes, and Coxeter said, okay, your paper is actually a few lines consequence of that. But if Heppisch had actually remarked that, then it would have been a disaster for us. Because the tools that he's actually using in his classification are pivotal for us because they don't exploit the global convexity, but they exploit arguments on the faces. And of course, we have many faces which are convex with angles of 120 degrees. We really have plenty of them, right? But there's two of them which are not. And we wouldn't know what to do with those. So if Heppisch had discovered the easy proof, we probably wouldn't have our theorem because, we would be lost in trying to understand without his insight. His insight was really fundamental.
And the other question I wanted to ask, Brachy at one point wrote a paper about a covering space picture where he tried to look at all the different possible soap films that might span a trefoil knot as minimizing separators between the sheets of a branch covering space over the trefoil knot. And this, he got including the film that only covers part of the boundary wire, is a minimum area separation between sheets of an appropriate covering space. So that, I don't know if how that picture relates to this Almgren minimizing definition of boundary, but
yeah, I don't know either. I'm not familiar with that work.
Okay, I
mean, if you send me a reference, I would be happy to take a look.
Right,
especially for me, it would be very interesting to understand, what kind of strategies we could possibly use for proving that these two objects, which we are uncertain about, are actually minimizing. It's really not clear to us how you prove that. Jean's proof of the minimality of the tetrahedron in the interior is a topological argument.
Since there's only one possible cone,
there's only one possible cone, which is not, invariant under, some translation, and that's the tetrahedron. And if you start with its skeleton, essentially, Jean proves you're not able to find a surface which bounds it and which has only triple junction singularities and nothing else. Yes.
So if you wanted to reproduce the step in her proof where the competitors are ruled out in the brachievolver, Ken has a built-in vertex popping command where you take one of these cones, and you essentially you blow a bubble around it and then remove one of the faces of the bubble. So is there a standard procedure for your cones on the boundary where you can replace the cone by something that will then evolve to lower area?
Yes. So we did have, this is where we actually were used by the experiments. So we do have a procedure to pop the central point in such a way that then, you evolve to something else. It doesn't always work that well, though, I have to say. And I wonder, probably for Brachie is the same. I don't know if it always works that well. So sometimes we just do things by hands, and sometimes we use actually this kind of automatic pop. We do implement that.
Yeah.
Giovanni, final question.
Yes. So first of all, Professor Lellis, thank you very much for the nice talk and for the deep and beautiful mathematics in it. And my question is the following. Is there any corresponding investigation in the Minkowski free space?
No, not that I know of. I don't even know if people have looked at Almgren minimizing in Minkowski space.
Okay.
I don't think so. Or the
Of course, there are results about minimal surfaces or maximal. They are also
right, exactly. So I was about to say, I guess you need to phrase the exact variational problem, right? Because that's an hyperbolic situation. So you're actually looking at kind of maximal surfaces. I'm not familiar enough to actually say, even if one could state something like Almgren's minimizing problem in that framework.
Yeah.
Of course, in a Riemannian situation, you can do it, and for Riemannian three-dimensional spaces, the local regularity theory is anyway, approximately Euclidean, so you will just get exactly the same theorem as Jean does.
Okay. But for example, considering space-like surfaces or space-like curves in Minkowski, it could be.
Yeah. No, I understand what you mean because I know a little bit about it.
I know.
But then I don't know in this level of generality how you set it up, if you can set it up.
Thank you.
You're welcome.
Okay, so Daniel.
Thank you. First of all, Professor Lellis, thank you for a beautiful talk. I would like to ask, is there any investigations in other situation when a tangent line can be like intersection is a half line or other situations?
Right. So we haven't yet started doing that. We believe our tools solve that too. But it's not a belief which is rooted on us trying. I mean, certainly a lot of the considerations would kind of be the same. A lot of the code is amenable to be changed, but of course, then one would have to check that you know everything really works in that case too, which I haven't done. But in principle, what we're doing is amenable to that. In principle, it's amenable even to consider, you know, gammas which are more general. So instead of being a curve, a smooth curve, if it is something which is piecewise smooth, then instead of the line L, maybe you would get, you know, finitely many half lines. And so you would get, instead of the point P and its antipodal minus P, you get finitely many points on the sphere, which are special. So in principle, a lot of the considerations could handle that too. But then, of course, at a certain point, you need to, like, you know, this algebraic fact, which kind of makes the number of solutions for the stationary problem kind of small. If you have too many of these special points, might go away. And then I don't know.
Okay, thank you. And one little question more. Can you say how to numerically check when the surface is Angren minimal? Or it's a long story.
Okay. So Brache, the surface evolver, is running essentially a gradient flow. So we run this gradient flow from a perturbation of the surface, if you want. Now, once you have discretized the surface, it's a gradient flow of the area functional, but because the surface depends only on finitely many points, it's essentially a gradient flow of a finite dimensional functional. So it's really like, you know, a bunch of ODEs that you're solving. Okay, so if, you know, in the proof, we kind of like, you know, in the code, we run Brache, and we change maybe the surface a little bit because otherwise it would be a stationary point of your gradient flow. We run Brache, and this is like, you know, evolving towards another stationary point, which is a triangulated surface anyway. So that triangulated surface, if it has less area, we can compute it. And that's what the competitor that we actually want to use to show that it is not minimal. Okay, now to really show that this is a valid competitor, you would need to show the existence of this map phi. Okay, that is difficult to explain. I mean, that needs quite a bit of considerations in low-dimensional topology. But essentially, you have a problem like you have this triangulated surface, you have your cone, and you want to know whether there is a Lipschitz map phi from your cone, which is also essentially a triangulated surface, into the triangulated surface over there. And if you can exhibit this map phi, the fact that the area of the final guy is strictly less shows you that you're not a minimizer.
Okay, thank you. Thank you.
You're welcome.
Okay, so let's finish by thanking Camillo again for the really nice talk.
Thank you.